Hi guys! Yesterday, a 6th grader asked me, what is calculus? Here is my 3-part response to her question. In the first part, I talk about the concept of infinity. Next is the concept of integrals, and then the concept of derivatives. Let's begin with the first one, the concept of infinity. This is our symbol for infinity. What does infinity mean? How many of you guys think of infinity as a very large number? Well, infinity is not a number. Infinity is a concept that something is unlimited, endless, or without bound. Let me explain. Let's say we are asked this question. How many numbers are there between 2 and 3? Definitely 2.1 is between 2 and 3, as well as 2.11, 2.111, or I can keep on adding 1 at the end of this number, and we'll always get a number that's between 2 and 3. And therefore, we now say that there could be an endless number of numbers between 2 and 3. And so that's our idea of infinity, something that is unlimited, endless, but infinity is not a number. So there are infinite numbers between 2 and 3. Now, let's talk about another concept related to infinity, which is infinitesimal. Infinitesimal is 1 over infinity. So what's the value of 1 over infinity? Let's begin with something that's familiar. Let's say I cut this pizza into 2. What I have is 1/2. Then I can cut it into 1/4, 1 over 8, 1 over 16, 1 over 32, 1 over 64, 1 over 128, and so on. Notice that I barely have pizza now at 1 over 128. How much more if I cut this into 1 over infinity? That is, one part cut infinitely many times. What would be the value of that 1 over infinity? Is 1 over infinity equal 0? Since infinity is not a number, then 1 over infinity is also not a number. What we have here is something that is just approaching 0, but not exactly equal to 0. And this is the concept that we are going to use in order to discuss the two main concepts in calculus, namely the integrals and the derivatives. Let's start with the concept of integrals. Let's say I have this triangle, and I would like to find the area of this triangle. Many of you would just say area is 1/2 times base times height. Well, that's correct. But we can also think of area not only in terms of square units, but in terms of other units as well. Let's say our unit is, instead of square, circles. Then we'll try to cover this red triangle with quarters. And there are how many of them? You can count each one of them, but the systematic way of doing that is related to the concept that I'm going to teach you today is, let's do the counting column by column. We have here 1 plus 2 plus 3 plus 4 plus 5 plus 6. And getting the sum, we have 21 quarters covering the red triangle. But the problem is, there are gaps in between. And so 21 quarters is not a very precise measurement of the area of this red triangle. There are parts that are outside the triangle, and there are parts inside that are not fully covered by the quarters. So what's our solution? How can we find a more precise area of this triangle using circular units? The solution is to use smaller circular units. From quarters, let's use nickels. And so let's cover the red triangle with nickels. In this case, we can add again 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. And the sum of that would be 36 nickels. Notice now that the gaps inside are smaller compared to the gaps here in our first solution. And we can say that the second one is a more precise estimate of the area of the red triangle compared to the first one. But still, there's a lot of gaps to be filled in. So what are we going to do? We can try using smaller circular units. This time, let's use dimes. So let's cover the red triangle with dimes. And there are 136 dimes all in all in the third triangle. And notice now that the gaps are very small compared to the gaps when we use quarters and when we use nickels. Now at this point, let's investigate the width of the columns. Here, this is the width of the column. For nickels, it's smaller. And for dimes, the gap is much smaller. But using now our concept of infinitesimal, 1 over infinity, we can now think of the quarter as 1 unit, and therefore the gap here is 1 over 1 or 1 unit, since the diameter of these nickels is 1/2 that of the diameter of the quarters. We now say that the gap here is 1/2, the diameter of the dimes is 1/2 that of the nickels, then this is 1/4. And if we continue making the width of the column smaller up to 1 over infinity, then we are using now the concept of infinitesimal. So if we now let the width of each of these columns to be 1 over infinity, then this is now the gap. Conceptually, we will not be able to draw 1 over infinity because that is infinitely small. But for our representation, notice now that we have here rectangles with a width of 1 over infinity. And that's now the idea behind integrals. Let's say I have here this weird looking shape. I want to find the area of the shape. The shape is not regular. We are hoping that there is a formula that we can use in order to find the area of this shape. But unfortunately, there is none. So what are we going to do? Probably we can subdivide the regions into composite figures like this and try to find the area of each of these parts. But if we are now going to use calculus, specifically integrals, what we are going to do is we are going to position this graph in our Cartesian plane, and we are going to slice the given region into smaller rectangles. And in the language now of calculus, this area cannot be represented by this formula, the integral of f of x dx from a to b. What does this mean? Let's zoom out one of these thin rectangles. So let's make it bigger. The height now of this rectangle would be whatever is the height of this curve. And that height is now our f of x, or a function that describes this curve. The width of this rectangle would be 1 over infinity, or another notation that we use for that is the differential dx. So we have here a rectangle with a height of f of x and a width of dx. And so what is now the area of this rectangle? It is the product of the height times the width, so that is f of x times dx, which is now this part that we have here. F of x is the height, dx is the width, and multiplying f of x times dx, that gives us the area of one of these rectangles. Then this elongated S shape is our symbol for integration. What this means is we are going to sum up all those small areas represented by f of x dx. So f of x dx represents the area of one of these tiny rectangles, and we would like to sum up all the tiny rectangles from lower boundary, which we denote as A, up to the upper boundary, which we denote as B. So therefore, this concise notation now is a way for us to say, sum up all the areas of the smaller rectangles from A to B. And by learning how to compute this integral, we'll be able to find not only the area, but also the volume of any weird-looking shape. And that's the power of calculus. Things that we cannot solve in regular algebra and geometry, we can solve in calculus. And since mathematicians are very creative in finding applications of all the tools that they learn, the application of integrals is not only limited to finding areas or volumes, especially when they discovered that finding the integral has an inverse operation, which we call as the derivative. It's like multiplication and division are inverse operations. In calculus, integration and finding the derivative are also inverse operations. And that will now bring us to the second concept that I would like to discuss with you today, which is the concept of derivatives. So what's derivative? Derivative is simply slope, but a special kind of slope. So to understand slope, let's say you tabulate the number of hours you study and you try to record what grades you got from those hours of study. Let's say your data is this. If you study 1 hour, your grade is 80. If you studied 2 hours, your grade is 90. And let's visualize this data. So let's have a point here. 1 hour, grade is 80. The other point is for 2 hours, the grade is 90. And let's connect it by a line. If we construct a right triangle connecting these 2 points, this is our rise and this is our run. The ratio of the rise over the run is what we call as the slope of the line. Some lines are steeper, some lines are flatter. Different lines have different slopes. We have positive slope, we have negative slopes, we have zero slope, and undefined slopes. Now, what if the scenario is now like this? You have a skater that's going down, and then going up, and then going up, and then going to the peak, relative peak, and then going down, and keep going down. How do we describe the slope here? Now, there's a problem because in order to find the slope, we need to have a straight line. And in here, what we have is a curve. So we have a problem. Second, the inclination here is steeper, here is flatter, then it goes up, it goes flat again, it goes down again. So it's hard to find the slope because there are different inclinations of lines. But we go back to our idea of infinitesimal. What if we limit our interval only at this point, that is 1 over infinity, approaching 0 but not equal to 0. So it's a very narrow interval. In that case, when you narrow the interval, curves can be turned into a straight line. In this case, therefore, it's possible for us to find the slope at this very narrow interval. And therefore, for each occasion, we can select a narrowed interval and we can find the slope of these points. And at that narrow interval, our horizontal change would be approaching 0. That would be 1 over infinity. It is not 0, but close to 0. And that concept now is what we call as the derivative. The derivative is simply the slope when the interval, that means the run, is too narrow that it is already approaching 0. And that is what we mean by this differential dx. And so geometrically, another way of thinking of dy over dx is the slope of the line tangent to the curve, or touching the curve at theoretically only one point. And by discovering techniques on how to compute this derivative dy over dx, where this dx is approaching 0, then mathematicians now are able to track small changes in locations and find the change in those locations. So you can now think of this curve, let's say, as the path of a missile. In here, the missile is going down, then it gains speed and going up, and then going up, and then going down. Or you can think of this as the behavior of the stock market. The market is declining rapidly. It starts going up, and then going up, and going up, and then flatten here, and goes back down again. And that's the power of calculus. We live in a changing world, and calculus is a very good tool in order to describe mathematically these changes. That's why we call calculus as the mathematics of change. Because if we know how to find the derivative, then we'll be able to find all these different changes, and we can quantify them and describe them in mathematical manner. So that's the second foundation of calculus, the derivative, which describe change. The first one was the integral, which enables us to find areas and volumes of irregular shapes. And by combining these two inverse operations and adding this as operations in your regular algebra, geometry, trigonometry, and pre-calculus topics, then you have a very powerful tool in order to solve problems of the world. And so when you study calculus, always bear in mind these two main concepts, the integral and the derivative. Everything that you are doing there, whenever you compute for the integral or you compute for the derivatives, either you are trying to find the area or the volume under a curve, or you are trying to track changes in the slopes of the lines tangent to a curve. I hope I answer your question. So we'll be creating series on this calculus for 6th graders, and we hope to see you again in our next video. Bye for now.